Yes.
Okay,
Now
can you hear me
yes.
now?
Apologies for the
Sorry.
people on the line.
Yeah, now we can hear
Okay,
very well.
so can I go on? Should I?
I don't know.
Well, you just started, I think.
Yeah, it just goes ahead.
Okay.
We missed a bit of the introduction.
Yeah, so sorry about that. I briefly introduced how massive black hole binaries are formed, and I talked a bit about the gravitational wave signal, and I just said that it will be important to us to find some electromagnetic constraints on the population and on single source of on single massive black hole binaries. So this is roughly the current stage. So here we have a bunch of candidates of massive black hole pairs at this stage. So you see that most of them are at a separation bigger than a kiloparsec. We have few candidates between the parsec and the kiloparsec, and basically no candidate at a separation smaller than a parsec. This is due to the fact that we can effectively resolve pairs at separation bigger than a kiloparsec. These are called dual AGNs, and dual AGNs are basically pairs of AGNs that are still not interacting with one another, so they are in the dynamical friction phase. So here you can see some images of confirmed dual AGNs, and of course we know them, but those are not really the sources we are interested in. I mean, they will put some constraints on the population, but we are interested also in the smaller separation range. So, okay, in binaries at smaller separations cannot be resolved through standard telescope, as they don't have the an angular resolution that is small enough to resolve them. Of course, we can use some other techniques such as VLBI. For example, this is an image of the shadow black hole taken by the Event Horizon Telescope. We can think of using the same technique to resolve binaries at smaller separation, for example, at 0.05 parsecs. But of course, we cannot think of using this technique among all the sky. I mean, the field of view is very small, and doing this for an all-sky search is not the most effective way. So what we can do instead is to find some massive black hole binary candidates through in-dark methods, and then maybe follow them up through VLBI observations. So in this slide, I basically try to summarize some of the signatures for the identification of supermassive black hole binaries. Of course, up there we have dual AGNs, and pairs at this stage can either be resolved by some of our telescopes, or can be found through uncorrelated Broad emission line variability and some continuum variability. I will speak a bit about the continuum variability in the following slides. As soon as the binary is formed, if the two black holes still have their own broadband regions attached, we can think of using some shifts in the observed Broad emission lines to find them. And moving to a lower separation, we can use, for example, some precession of the jets, some modulation in polarization, search for some periodicities, using some echoes from the Broad emission lines or the lasty torus. And as we move towards the gravitational wave dominated range of separation, we will have chirping signals, meaning that the separation will shrink pretty fast. And so we'll do the orbital period. And after the merger, we expect some post-merger signatures, but I'm not really an expert on that. So, okay, let me just give you an example of what we expect in spectroscopy. So, for example, I said that we have some line shifts. So, while the binary is forming, each of the two black holes will have its own Broglie region attached to it. Since we have an orbital motion, the Doppler shift will cause the emission from one of the Broglie region to be shifted in the spectrum. Since the motion is periodical, we expect the line shift to move with the same period as the orbital period. So this is basically what happens. As the two black holes move, the profile of the Broad emission line will change. And if we take, for example, the position of the centroid, we we expect it to move towards the left and the right with the same period as the orbital period. Of course, our ability to identify such signature will strongly depend on the separation. Mean that if the separation is too large, the period will be too large, and we are not able to resolve them on a human timescale, so let's say. So a possibility is either to search only for small separation binaries, or to use another signature for larger separation that requires a smaller time and is based on the uncorrelated variability of broad emission lines. So since we have two broadening regions, and if we assume that both the black holes are active, the total profile of the broad emission line will be composed of two contributions, one from one black hole and the other from its companion. The two black holes are still not interacting, meaning that the continuum emission is not affected by the presence of the other. And so the variability of the blue contribution will be uncorrelated with the one of the red contribution. So if we perform a reversion mapping, so if we take the line profile as a function of time for a certain period, we can build the light curves from different parts of the broad emission line and then check for their cross correlation. This has been done on some simulated data. So this line, the dark blue one, is from a real source. And the others are from some simulated light curves where basically the other state took the signal from this one. They shifted it by alpha period of a period that they assumed. They built the total profile for the emission line as the sum of the two components, and then basically took the light curve of the two. They divided the broad emission line in different regions, and they took the cross correlation between all the light curves from each region. And as you can see, if we have a binary, so in this case, the cross correlation tends to decrease towards the center, while in the single massive black hole scenario, the cross correlation remains pretty high at the center. This is due to the fact that at cutting the broad emission line at the middle, we're basically effectively dividing the two contributions in the maximum way possible. So this is a brief example of what we can do in the spectroscopic side. And now in the rest of the talk, I'll talk about my contribution in the field up now. So I'll talk a bit about the continuum variability and the periodicity detections. This has to do to photometric signal rather than spectroscopic ones. And then I'll go back to spectroscopy to talk about a possible signature from broad emission line echoes. So let me start from the largest separation. So as I said, this test to find pairs has to do with the continuum variability. We know that AGNs are intrinsically variable in all the bands, and that this intrinsic variability is pretty well described by red noise. So a stochastic process that introduces long-term correlations in the data, and that is known to mimic some periodic behavior. And this is why the red noise, as I will speak more about it later, makes the periodicity and identification pretty difficult. But on the other way, we can try to use the shape of the power spectrum, meaning the shape of the Fourier transform squared of the signal, to search for massive black hole pairs at large separation. So I'll focus on the optical band to start. In the optical band, the noise is pretty well described by the so-called dampened walk. This is a stochastic process that has a power spectrum that is flat at low frequency, and then decreases as the frequency to the -2 as soon as we get over a breaking frequency that is associated to a damping timescale in the time domain light curve. So here you can see some example of this power spectral density. Here I'm just changing the normalization sigma. Here instead I'm changing the damping timescale, so you can see that the power spectral density breaks at a different frequency. And an alternative description of the noise can be done using the covariance function. So instead of going through to the periodogram or the power spectral density, we can use the observed light curve and check for the covariance of points at different delays from the one we are starting. For example, we start here and check the correlation between this point and this point, this point and this point, and so on. And this basically enters the tau ij here. So what I said up to now is true for a single AGN, but what we asked ourselves is, what if there are two AGNs and we are not really able to resolve them with our telescopes? We assume that the contribution to the observed light curve from each of them is uncorrelated, and if that's the case, we can write the power spectral density of the new signal as the sum of the power spectral density from two different walks, and that in the same way, the new covariance function will just be the sum of the covariance functions of the two different walks. So with this new description, we can try to make some model comparison. We need to check if the light curve is better described by a noise with this covariance function or this covariance function, and check if we are able to find some unresolved duos or UBHTs, as we call them here. So in order to do this, we basically sample two kind of light curves: single massive black hole light curves, where we have where the light curve is just a realization of a dampened walk, and a UBHT light curve, where the total light curve is the sum of two dampened walks realization. We assume two different samplings. The blue one is sampled for 10 years every 3 days. And in an even sampling, we introduce some window where we are not taking any data during the 10 years. This is basically done to mimic what you expect from LSST. So if we combine all the bands, we expect a point around every 3 days. And so, yeah. To analyze this light curve, we can do two things. The first one is to compute the periodogram, as I showed you before, but that's not really statistically robust, meaning that if the sampling is uneven, the inference using the periodogram will be biased, as we are introducing some correlation between the different frequencies at which we compute the periodogram. An alternative way is to stick with the time domain light curve and use, for example, Gaussian processes to describe the observed stochastic signal. So what we do is to perform a fully Bayesian analysis by means of nested sampling in order to compute the evidences of the two models, where the evidence is defined as the integral of the likelihood weighted of the prior distribution over all the possible parameters, where the likelihood is the one given by the Gaussian processes that are basically statistical tools that generalize the generalized distribution up to functions and not only on random variables. And these are basically one of the best tools that we have to describe stochastic signals in time series. So we assess which model is preferred by means of the bias factor, that is basically the ratio between the evidence between two competing models. At the numerator, we will have the UBHT model, so two AGNs, and at the denominator will have a single AGN, so a single dampened walk. So we assessed how many false positives we have using this method. To do so, we sampled 1,500 single massive black hole light curves. We filled them with both models. We found those that are incorrectly identified as BHTs by imposing a bias factor threshold of 3. That is basically the threshold to which the evidence in favor of the modular denominator becomes to be significant. So doing so, in the even sampling scenario, we find that only the 0.2% of light curves are incorrectly identified, so as are false positive, and this fraction goes up to the 0.6% in the uneven sampling scenario. These are, to me, still pretty low. I mean, we have 3 light curves among 1,500 in the even sampling and 9 light curves in the uneven sampling. So the most important thing to this work is to understand whether this can actually identify some UBHTs. The main conclusion is that we can, though in a small region of the parameter space. So you can see that all these are UBHT light curves, and the one with the stars are the ones that we are able to identify as UBHTs. So basically, this happens when the damping timescales, so the breaking frequencies at where the power spectral density starts to go as the frequency to the -2 are very different, with a ratio smaller than 0.2, and where the amplitude of the variability is pretty similar, with a ratio bigger than 0.2. To understand why this happens, we can take a look at the power spectral density. So if we take a look at it, you can see in orange and green the power spectral density that you expect for a single Doppler walk, and in blue the one from a double Doppler walk. And as you can see, the shape of the power spectral density for this combination of parameters starts to deviate from one of a single Doppler walk. In particular, we have a sort of second plateau forming between the breaking frequencies. So basically, the test is able to identify UBHTs as soon as the shape of the power spectral density deviates strongly from the one of a single Doppler walk. So this is basically what I wanted to say for the large scale pairs. And now I'll delve more into the smaller separation massive black hole binaries, and in particular, I'll talk about periodicity detections. So considering massive black hole binaries, we expect some periodic modulation from different physical processes. In particular, we have some periodic feeding from a circumbinary disk that forms as soon as the separation becomes of the massive black hole binary becomes small enough. We have some relativistic effects, such as the Doppler boost, that beams the light along the direction of motion, giving rise to a sort of lighthouse effect. And if the binary is seen as nearly edge-on along the line of sight, we expect also some effect from the gravitational self-lensing from the accretion disk of one of the two black holes passing behind the companion. So since we have different physical origins, we also expect some different shapes in what we observe in the inner light curves. In particular, considering the periodic feeding, we expect some light curves that are sawtooth-like, meaning that there is a sharp rise and then a slow decay. Concerning, for example, the gravitational self-lensing, we expect some flares that are basically when the accretion disk passes behind the companion. And only in the case of the Doppler boost applied to circular orbits, we expect some sort of nice sinusoidal periodicity. So we start to understand that the searching for periodicity is pretty complex, since we have all these shapes, and is further more complicated by the presence of red noise that can mimic it. So what we usually do to find some periodicity is to compute the Lomskardo periodogram. So we compute the periodogram of the light curve and search for a peak in the periodogram, and the frequency associated to the peak will tell us something about the period of the signal we are observing. If we have a single sinusoid, we expect to have a single peak pretty high, and as soon as the shape of the light curve changes, for example, considering a sawtooth-like light curves, the power in this peak gets distributed among the harmonics. So the amplitude of these peaks becomes lower, and it can happen that This is basically below the noise level that we have in our light curve. In particular, recently, Lin et al. Did a study on the efficiency of the long-scale periodogram to find massive black hole binary light curves in presence of red noise. And what I found is that in idealized case, so as a light curve sample for 3 years every day, only the 24% of sinusoidal light curves are correct to retrieve, while concerning the sawtooth light curve, they retrieve only the 1%. So we tried to use an analysis similar to the one I presented before, where we use Gaussian processes, where instead of having covariance matrix that is just the one of a dampened walk, we have some information about the periodicity. Okay, so in order to describe periodicities, we have two ways. We either use an analytical formula as the mean function of the Gaussian process. So the stochastic process will move around the mean function that we are basically deciding. Or we decide to ignore the analytical formula since we don't really know the shape of the periodicity and introduce the information about the signal being periodic in the covariance function. We opt for the second method, and we have two possible ways to introduce this information. We can either use a covariance matrix that is proportional to the cosine of the time difference between 2 points, but this suffers somehow the same limitation of the periodogram, meaning that it can retrieve the correct period, but it can describe the shape only for nearly sinusoidal light curves. So you can see here that the red line covers pretty well the signal, but concerning a sawtooth light curve, the period is the right one, but the shape is completely different. And having a different shape would affect the evidence of the model, and thus will affect the bias factor. We therefore opt for a different kernel, a more general one. We have an additional parameter, a length scale, that basically allows us to describe rapid changes in the periodic term. And with this kernel, we have enough flexibility to describe both the sinusoidal one. Now you can see that it is purple rather than red and blue. And we can correctly describe also the shape in the sawtooth scenario. Also, just to show you another example, I said that for the gravitational self-tensing, we expect rapid flares. And you can see again that the cosine kernel gets the right period but the wrong shape, while our new kernel, our new covariance function, can also describe such rapid changes. So we performed the same analysis where compared it to the work by Lin et al. And we did it in two ways. The first one, we set a bias factor threshold that allows for the same number of false positive as in Lin et al. And in this case, we find the ideal scenario, the 53.3% of periodicity are correctly retrieved compared to the 24%. And more interestingly, we retrieve around the 58% of sawtooth light curve rather than the 1% in the Lin et al. Work. When we consider a more sparser scenario, like this, more similar to what you expect from the PTF, we retrieve the 23.4% for the sinusoid, while they retrieve the 45%. And in the sawtooth light curve, we retrieve around the 9% as they do. I think that is still not clear to us is the fact that as they decrease the number of points in the light curve, they have an increase in the fraction of retrieved periodicities. But still, considering this case, they will have a higher fraction rather than our method. We then used some light curves more similar to what we extract from LSST. So this will be the whole LSST campaign. These are the duration of the light curves that I showed you before. And in doing so, we retrieve around the 51% for the sinusoidal light curves compared to the 23%, and around the 65% for sawtooth light curve compared to their 1%. So it seems that considering an arbitrary shape informed in the covariance function is allowing us to find more periodicities than what they find. The second way in which we set device factor threshold is using a log curve. So basically we find the true positive fraction as a function of the false positive fraction, and we set the threshold at this point. They're basically the more distant from the one-to-one curve, and this point basically allow the ratio between the true positive and false positive fraction to be maximized. Using this new threshold, we have this result. So in the LSS case, the sinusoidal ones go to the 70%, and in the sawtooth around to 78% compared to the 24 and 1. In the PTF-like, we have 53 and 26 compared to 45 and 9. And the LSST-like, we have around 60% and 69% compared to the 23 and 1%. So you see that using this new algorithm, let's say, we can find some a higher number of periodic signals. Okay, now I changed the way I said this. So before I was talking about massive black hole binary signals, now I just said periodic signals. Well, because in general, it is not said that the periodic signals are generated only by massive black hole binaries. Periodic signals can be generated also by single massive black holes, for example, by the precession of the disk around the spin of the black hole. Okay, a small parenthesis on LSST. In few months, I hope, LSST will start taking observation. It will take observation in 6 bands. And as I said before, if we combine all the bands together, we'll have an observation around every 3 days. And what we are working on right now is to build a multi-output quotient process that will allow us to do the same analysis, but informing one light curve with the points of the others. So we will not combine all the points in a single light curve, as the parameters of the noise will change depending on the band that we are considering. But we are trying to inform everything together in a single Gaussian process. So I said this before, and the main point for which I was saying this is that to be sure, to effectively looking at the binary, we cannot be happy just with a detection of a periodicity in the photometric light curve. We need something else, and that something else could be either the a gravitational wave counterpart, but we'll need to wait for that, or we can look for something in the spectroscopy. And for this reason, I will talk about the test that we proposed that considers the echo from the Brode emission line of a signal coming from a massive black hole binary. In particular, when the two black holes are close enough, they will be surrounded by a single Brode region that responds to the signal of the two massive black holes combined. Of course, this Brode region can have a certain emissivity profile, and in this case, we assumed it to have a spiral arm just to allow it to describe nearly all the Brode emission line profiles that we observe in spectroscopy. And we assume the Brode region to respond only to the Doppler boost signal of the binary. And now I'm working on generalizing it to the self-sensing. We will be missing again the periodic feeding, but let's stick to the Doppler boost up to now. So what we find is that, of course, in the binary scenario, the emission will be anisotropic, while in the single massive black hole scenario, the emission will be isotropic. And if we build the broad emission line by summing up the contribution from all the elements in the broadband region and consider only the tails of the broad emission line, so we integrate the flux here and here at different times, what we find is that considering the binary scenario, we have a nearly alpha period delay between the response of the blue region of the broadband region and the red region of the broadband region. This is due to the fact that the emission is anisotropic, so sort of lighthouse, and basically, if we consider this element of the broadband region and the massive black hole that is emitting the most, emitting here at that moment, the other element will be illuminated alpha period later. The same doesn't happen in the single black hole scenario, as the emission will be isotropic, so these two elements will be illuminated nearly at the same time. And in fact, we observe nearly no delay between the red and blue part of the broadband region. So this can be used as a sort of signature of the effective presence of a massive black hole binary in the spectroscopy to confirm what we find in photometry. So yeah, these are basically the conclusions. We proposed a new identification method that leverages agents intrinsic variabilities for massive black hole pairs at large separation. We proposed a fully Bayesian flexible method to search for periodicities with arbitrary shape in presence of red noise. And lastly, we propose a possible binary mixed spectroscopic signature that can be used to confirm the nature of a periodic source. And yeah, that's it. And if you're interested, check the papers. They're all in the archive. So yeah, thank you.
Questions?
Very interesting studies. I have two questions. The first question is about the delay, the light type of the broadline region, but also the analysis that you described in the first part of your talk of cutting the broad lines in different segments and looking for the delay. This analysis, I have the feeling that it assumes that the broadline region is uniform. Because if there are condensation, if there are any difference in the density, you may have the red part of the BLR being brighter or fainter, depending on if it's denser or less dense. So won't this include an additional noise term in the results in the analysis?
Yes, and to sort of take care of this, we assume this kind of broad emission line emissivity. So this parallel arm could, in principle, describes what you're saying, so different densities in the broadband region. But okay, so here a given shape just to describe what you observe in the broadband emission line profiles. But yeah, you're right. So having different emissivity profile could change what you see.
Mm-hmm.
So, and this is something that we are working on right now. So we are going to assume different broadband different emissivities, adding up also the self-lensing effect, and check that what we'll find not only in these two parts of the broad emission line, but also in centers.
Yeah, exactly.
Just to see the contribution from different regions.
Exactly. And the second question is about the analysis with Gaussian processes. Again, here, what happens if you account for stochastic variability of the AGN? Because the AGN also shows some stochastic variability.
Yep.
So in the Gaussian process, it's only the periodic component, if I understand.
No, in the Gaussian process, we have both.
Ah, okay.
Yeah, so let me put here. So basically, yeah, sorry, I didn't specify that. When I said periodic model, we have the sum of the periodic model and the covariance part, the double.
Okay.
Yeah.
Okay.
So we are basically taking both of them into account.
Okay.
Sorry about
Okay.
that. Yeah.
Okay, good. Great. Thank you.
So I have one on the light echoes.
Mhm.
When in the Doppler boost scenario, do you assume that both black holes emit, or is
Yes, we assume both of them to be active. So this kind of signature will be most visible when one of the two will emit much more than the other, just because when assuming like an equal mass ratio, the effect will be smoothed out because both of them will contribute in the same way. So we'll basically have the same mean value for the flux and the correction. So, sorry, this effect would be a second order effect. So not really visible if we add some noise. But yeah, we are assuming both of them to be active with different mass ratios and different Eddington ratios. Where the Eddington ratios are set by hydrodynamical simulation after we decide which mass ratio we are using. Yeah.
So it's dominant when, for example, the secondary is dominating.
Yeah.
Something like that.
So the secondary is expected to have an higher mass Eddington ratio, and then it will have a higher luminosity. So
Yeah, when you are comparing your results with lean et al, right? About like sawtooth and sinusoid. So as you said, it is surprising that when you have PTF-like data set, which has like gaps, it like gets more of those binaries, like 45% or 24%, right? I think that is because because there are lots of gaps. If there is no signal, it will still get lots of there will be lots of false positive also. So instead of just looking at like what percentage is taking back, should not do like a false positive, true positive study that will give us a better sense of what is happening.
yeah, I agree with you. But if I remember correctly, and maybe Maria, you can confirm that these fractions are for periods that are in a given range from the injected ones.
Yeah,
So
in this paper, we didn't look at the false positive rate. We set the threshold and we say how many can we detect.
Yeah,
I think you're right that if we had looked at the false positive rate, it would be much worse in PDF. And my understanding of why this happens, and for the very poor example right here, you get the boosted factor, is practically the periodogram does something like a chi-square fit. Imagine you have very well sampled light here. You have the sinusoid or whatever periodicity you have, and then you have the red noise on top of it. So you cannot fit it very well with the sinusoid. So the peak of the periodogram goes down. And then you introduce the very sparse data from PDF, and then pretty much you can fit anything.
No, I understand. That's why I said like maybe doing a like false positive for this study will be like more like actually saying what is actually happening.
I agree, but the point of this was like the periodogram cannot pick up the non-sinusoid of it.
And I think like, can you do like a harmonic summing of the periodogram to make it better?
There are tools like the multi-term periodogram that would allow you to fit with multiple Fourier components, like multiple, try catch the shape.
Any more comments from the audience or online? You can see I'm raising. I have one basic question. When you were evaluating, I think it was the contamination, between the selection for singles or doubles, I think that where you were quoting a very specific value of 0.2% that you were very sure at what level. I imagine that depends on the kind of like the signal to noise of your data.
yeah, that will depend on
what is the quality of the simulations? I mean, it's like infinite signal to noise, or
no. This is more like what we expect from LSST, so the same signal to noise ratio from LSST, and we didn't do a proper signal to noise ratio study here. We just changed the length of the light curve. So, for example, changing the length of the light curve, this threshold goes up. No, sorry. But this region of the parameter space shrinks. But yeah, I think that doing a proper SNR study would be pretty interesting. Yeah. But yeah, still, we did that only for SST like noise. Yeah.
Can I follow up on that? This 0.2% is only for this region of the parameter space or the entire parameter space?
The 0.2% in the false positive, you mean?
Yes.
No, it's for this kind of parameter space, the whole one.
Really?
So, no, wait, I mean, let me rephrase it better. So, for the false positive rate, we consider only supermassive black hole cases. So, this is the parameter space we are using. And we fitted it with both the single and the double damper work models. So, this is the parameter space for the false positive. This parameter space can be defined only for the double damper work one.
It just sounds too small. I mean, I would expect to have, I mean, the false positive rate I would expect to be much, much larger. 0.2% is extremely small.
Yeah.
Given how narrow,
Small, like something very rare.
Yeah.
You want to minimize your false positive rate.
you won't, but given the analysis looks too good to be true. And given how narrow the range of the parameter space in which you are sensitive, because all the rest of the parameter space, you are not sensitive at all.
Well, that would be false negative though, not false positives. Right.
Yes, but still is
Let's say, so if we have a single damper wall case, to me, the periodogram would look like this. And basically, this kind of periodogram is effectively classified, would be classified as UBSD if the parameters of the UBSD are around here.
Yeah, right.
And here, the model cannot find them. So maybe that's why we have such a small fraction of
Okay, yes, yeah, okay, fine, yeah. Because you really narrowed down
Yeah.
your, yeah, okay.
Yeah.
Okay, yeah.
Okay, if not, there are no more questions, let's thank again